Next, let's look at another rendering resource, particle systems that emit meshes. This is actually something we touched on in last year's discussion. Back then, we observed the phenomenon, but we couldn't clearly identify the root cause. Since then, we've encountered similar patterns across multiple production projects, and through controlled testing, we were able to isolate the problem. In Unity 2022-based projects, we frequently observed unusually high memory consumption in regions labeled Graphics No Name or GFX Device GLES, rendering segments. When we inspected these cases using Memory Profiler, the pattern became very clear. In many projects, mesh-emitting particle systems were the primary contributor. For testing, we reused the monster model mentioned earlier as the emission mesh source. We activated a particle system that continuously emitted instances of this mesh. Before and after activation, memory usage increased dramatically. In some cases, a single mesh-emitting particle system introduced tens of megabytes of additional memory overhead. Our hypothesis was that temporary mesh instances generated by particles were not being efficiently reused. Let's look at the numbers. The system configuration limited maximum particles to 50. That means at most, 50 child particles should be active simultaneously. However, when we calculated theoretical memory usage, the result did not match observed allocations. Interestingly, Memory Profiler did not clearly classify this memory as mesh-type allocation. This makes the overhead somewhat opaque. We could only conclude one thing: mesh-emitting particles can introduce significant hidden memory residency. We then tested potential influencing factors. First, we suspected GPU instancing. We enabled GPU instancing support, but surprisingly, there was no meaningful improvement. Next, we tested particle system count. When two identical mesh-emitting particle systems were played simultaneously, memory consumption increased more than linear scaling. The overhead was larger than simple doubling. Third, we tested mesh complexity. When replacing the model with a smaller geometric mesh, memory footprint decreased noticeably. Fourth, we reduced emission particle count by half. Memory usage also decreased, but not proportionally. This leads to a practical question: how do we reclaim this memory? Based on our current observations, in the latest Unity 2022 releases, this behavior still appears unresolved. In our view, it should be considered a potential engine-level defect. To avoid this issue, the safest strategy is simple: use mesh-emitting particle systems sparingly. This is especially important for mobile devices, low-end hardware tiers, memory-constrained runtime environments. Another important observation is memory recycling. In many cases, destroying the particle game object itself does not guarantee memory release. The memory may remain resident at runtime. In some situations, explicit resource unloading via runtime APIs may be required. However, calling aggressive unload routines, such as RUA-style cleanup, can introduce significant performance overhead. From a cost-benefit perspective, it is usually not efficient to trigger heavy manual unloading logic just to reclaim particle mesh memory. Therefore, the practical recommendation is prefer smaller mesh assets or avoid mesh-emitting particle systems when possible. Across this entire section, we discussed several rendering-related resources: shaders, render targets, video playback systems, and mesh-emitting particle effects. The key insight is this: rendering memory consumption is often much higher than developers intuitively expect. System-level allocations can be introduced by shader variant runtime program generation, render texture buffering pipelines, video playback decoding and rendering stacks. Engine-level non-standard allocations may also appear in particle simulation systems, renderer batching structures, cube map environments, compute buffer pipelines. The best optimization strategy is not to treat memory as a single metric. Instead, analyze rendering memory holistically based on the real workload characteristics of your project. And one more small note about a known issue. In early Unity 2022 versions, there was a memory leak related to the serializable reference mechanism. This could cause object leakage under certain serialization workflows. The issue has been addressed in newer engine releases. If you encounter unexplained memory growth under native Unity subsystems, no-name objects, consider upgrading the engine version as a first debugging step. That concludes this section.